Okay. Hi everyone, thank you for being here at our third Cosmic Conversations talk, and today we're going to have a little bit of nuclear physics. Cornel is doing his master's at the moment, but he did his honors project on this topic, and it relates to cosmic muons, quantifying how much of them get through a mountain, and asking, can you actually build an underground lab, given what he's found. So yeah, over to Cornel.
All right, thank you for the introduction, Jared. And pointer options, data pointer. All right, so using Geant4 to establish the viability of the South African underground laboratory considering cosmic muons. I've tried to get the title shorter, but that's about as short as I got it. So if you have any suggestions, please. All right, so first a bit of background. Why are we going underground? So there's interest in developing an underground research laboratory for high energy physics and other matters in the Southern Hemisphere, and South Africa is such a candidate. One of the possible sites for such a facility would be the Huguenot Tunnel, which is what was on the covering slide, as you can see there. So there's your normal tunnel that carries traffic, and then there's a northern tunnel as well, which was used for sort of testing and pre-construction. At the moment, that tunnel's empty, and I'm looking into if we can hypothetically establish a laboratory there and comparing this to other similar facilities. So why are we heading underground to begin with? Well, some experiments want very little background radiation. Such experiments include dark matter detection and neutrino oscillations. And the Earth is constantly bombarded by cosmic radiation, so we might want to do something about that, and well, we're going underground for that. So the most penetrating components are muons and neutrinos. We're focusing on muons because they simply interact more with the neutrinos, and it's a lot harder detecting neutrinos. All right, so first we're going to need a tiny bit of background on how charged particles such as muons interact with matter. So usually this is quantified using the stopping power. This is a measurement of the energy loss per length traveled in a medium to the This is the electronic stopping power, which focuses on the energy loss to the electrons through inelastic collisions. This is a Bethe-Bloch formula. It's there. You can look it up. It has a lot of extensions, and it's pretty versatile. However, it has some shortcomings that you need to take into account, and that's simply that at high energies, the Bethe-Bloch formula doesn't take into account some radiative processes, these being pair production, bremsstrahlung, and photonuclear interactions. Luckily, these scale linearly with energy if you formulate them correctly, and then you can formulate a total stopping power, which is what you see there. And here we can see the total effective stopping power of muons traveling through copper. And here you see the Bethe-Bloch formalism. What it does, it sort of levels out here at about 100 GeV, and you see it sort of plateaus. In the meanwhile, the radiative losses, they in turn start to grow linearly and become dominant at some high energies. Another point to note is just this point right here. That's the critical energy. That is where the radiative losses and the collisional losses are the same. And using that A and B value, we can make an approximation of the range known as the continuous slowing down approximation range. A and B are slowly varying, so we can assume they're constant, and from there on out, we can just slap an integral on it and get this formula for a rough estimation. All right, so I should probably mention what a muon is. So the muon's like an electron and positive or negatively charged lepton, but it's much, much heavier, about 200 times. This means that it suffers from significantly less bremsstrahlung, so it has a much better penetration and range. How are they produced? Well, the cosmic showers are mostly protons and alpha particles, and these interact with the high atmosphere to produce pions and kaons, and those in turn decay to produce muons, as you see here by these channels. Now, muons aren't stable. They have a lifetime of about 2.2 microseconds, and they do decay to electrons. Luckily for us, we don't really have to worry about that because, well, the high energy ones we're looking at simply don't have time to decay. Another topic worth mentioning is the charge ratio. This is simply just the ratio of positively to negatively charged muons. It's a graph of that, and you can see it's mostly positively charged muons, and this is simply because the cosmic radiation itself is positively charged to begin with. Next, we can look at the energy distribution of the muons real quick. So this is the muon differential flux, and here are a bunch of different experimental measurements, a reasonable agreement. Then you see this solid line, that is a, let's just say, more precise analytical approximation. And then you see this dotted line here that we are interested in. This is Geiser's formula, which makes a handful of assumptions, such as the curvature of the Earth is negligible, the muons are mostly coming in vertically, and they all have high energy, which luckily for us is actually the case. And then we end up with this formula over here. No need to worry too much about it, but what we can do with it is we can integrate it back using some energy bounds to get an idea of the flux if we have an energy cutoff. And now what are we going to do? We're going to try and find that energy cutoff using Geant. Then just a quick mention of some of the sort of standard materials that you're going to encounter in the literature. It's standard rock and water. Standard rock is just defined as atomic mass 22, atomic number 11, density of 2.65 grams, so very close to just silica. Our sandstone's a little less dense, but we decided to not focus too much on the standard rock measurements because the water is a bit more generally used. So for the water, meters water equivalent, it can be defined as the range of the lowest energy penetrating particle in water. So if you have that you need a muon of energy 1 GeV to get through a barrier, then you convert that 1 GeV to its range in water, and that's then your meters water equivalent depth. There are some other ways to quantify this. Some of them use flux, and this is essential because you need to take into account the shape of your overburden. So for us, it's a mountain. Other places might have, for example, just in a mine, a flat overburden. And what you need to take into account is that for a mountainous overburden, if muons come in at an angle, they're going to traverse less of the overburden and as such have a lower energy. So if you're doing it experimentally, you'd likely want to use that instead. And then I should also at least mention that when you are considering a tunnel versus a mine, there are a significant amount of engineering challenges to take into account as well. With the Huguenot Tunnel, if you want to establish a laboratory, you sort of just drive in, drop the equipment and people, and you leave. Meanwhile, if you want to go to a gold mine in Gauteng and establish a laboratory there, you're going to need a very sophisticated and very heavy-duty and very safety-proofed big elevator. And that costs money, of course. All right, so here's just a graph showing you the conversion factor, which is just how you switch from water to standard rock to some slightly less standard rock. And on the left-hand side, you see some facilities along with their kilometer water equivalent depth and their minimum muon energy that they need to get to that depth. Do note the Sudan Minos detector or facility in Minnesota. We'll come back to that later because it's quite close to what we find in the end. All right, now I can actually get to Geant, which is why I'm here. So quoting their website, Geant is a software package for the simulation of the passage of particles through matter using Monte Carlo methods. So what this means is, well, it's a simulation package. You build your world, you build your experiment, you build your physics that you're going to be using, and then you run your digital experiments. So it's developed at CERN, it's written in C++, and there's just a few things I should at least mention over it, even if we're not going into the details. First is the physics list. This is just what type of physics are you trying to simulate. So for our case, it would be, for example, muon ionization, muon bremsstrahlung, muon pair production, and muon photonuclear reactions. What are the exact mechanics of all of those? I'm not 100% sure because that went a bit beyond the scope, but you can use those in FTFV-BERT, which is a pre-built physics list. So this is convenient because it's pre-built, it's properly tested, and it includes all the effects that we require. Another matter that should be discussed is production cuts. So as you can imagine, with these very, very high energy muons moving around, you produce a lot of bremsstrahlung. And if you try and simulate all of that, your computer is going to complain a little bit. So what they have done at Geant, and this is how they treat infrared divergence as well, is that you sort of have a cutoff. This is either an energy cutoff or a range cutoff, but essentially what it means is that if a particle would have a range less than your cutoff, then you simply don't generate that particle, so you don't have to spend CPU time tracking it. This means that that energy is instead just marked as being lost to the medium at that point. So we can actually use a very, very high cutoff because we're only interested in our primary muons. In the end, I think we settled on 10 meters. So this means that any secondary particle of range less than that will simply not be generated. And this saves a lot of time, especially for visualization if you want to try that. Next, just a quick rundown of how the simulation works. So you've got a run, which is a set of events, and the event is really the unit experiment. You launch your muon and you track it until zero momentum, so until it comes to a standstill, until it decays, or until it leaves your world volume, as well as all the secondary particles that it generates. And that's really the core unit experiment of what we're doing. Next is the track that just does as it says. It tracks individual particles, marks down where they are, what physics they need to undergo in this medium. Are they in a magnetic field? Do they need to take that into account? And step is just the time unit propagation. So you just move the particle by a tiny bit, update its properties, its velocity, acceleration, and all that. All right, so because we're doing something computational, it's usually a good idea to at least have some sort of quality control or confirmation of what we're doing. And we decided to try and replicate this experiment. This is 1 tera-electron-volt muons passing through 3 meters of iron and recording their momentum at the end. So this was done in the Geant4 Monte Carlo code, and we tried replicating it in Geant. We weren't able to get it exactly the same, but we got fairly close. So our median and our mean values agree well. The general shape also agrees sort of, but as you can see, the full width at half maximum is quite different. One of the possible reasons is simply because those high energy radiative processes have very high stochastic effects. So it's possibly something that's just how the different codes handle those processes differently. But nevertheless, it's relatively consistent. All right, so now we get to actually look at the tunnel, and what you see is there's a granite base and sort of a sandstone cap. In the end, we went with these compositions for our materials, for Geant, which needs that, and then we just started simulating that. So what we do is we basically have a parameter space of the thickness of the overburden and the energy of the muons. So we essentially just start iterating over that and explore what happens. So this is the simulated setup, which isn't too different from the mountain. It has a granite base of about 300 meters and a sandstone cap. The trapezium is about 500 meters wide. And here at the bottom, you see a tiny couple of extra white lines. So what's going on there is you just have a 5-meter opening of air and an idealized detector. And the idealized detector does exactly that. It's idealized and just records what muons are hitting it and what are their energies and so forth. And what we do is we then start here, start blasting it with 100 GeV muons, see what happens, increase it to 200 GeV, see what happens, rinse and repeat until 1 tera-electron-volt. And then you just move on over to a slightly thicker overburden, and you repeat the process until you get all the way to the thickest overburden of about 800 meters. And in the end, this is what the results look like. So you've got your position, which is a measurement of the overburden, and you've got your primary energy. And then here on the graph, you have your counts of how many of the muons made it through. So for example, you see for the thick overburden, none of the 300 GeV and below muons made it through. And then what we're going to try and find from here is simply where did we get a 50% penetration rate? And that energy will then be our minimum energy that we use. Of course, you can also look at the energy of the muons that do arrive at the bottom. Unsurprisingly, thicker overburden leads to lower energy muons. It sort of screens off all of the high energy and medium energy ones. And yeah. Oh, you missed most of it, Leroy. And yeah, at the end, this is our final result, which is just a measure of, at the thin overburden of about 300 meters over the granite, you need about 228 GeV, which leads to this muon flux and which leads to a water equivalent depth of about 756 meters. Similarly, for the thick overburden, you need about 720 GeV, and you get this flux, and you get this meters water equivalent. And what you see in the end is that these values that we obtain are very close to what was obtained at the Sudan Minos detector in Minnesota. So to condense the entire project, we basically were able to just say that, yes, it would be feasible and it would be comparable to that specific detector. Here is just a show of some of these detectors throughout the world. So this is where the hypothetical facility would lay. And here's a Sudan Minos detector. And of course, then you get some of the deeper ones. So yeah, that's a bit shorter than usual Cosmic Conversations talk, but that's about where it ends. So Geant4 was quite useful in examining these tools, the scenario, the facility would be comparable, and of course there's a lot of things you can do extra. So you can look into simulating the cosmic rays from their origin in the higher atmosphere to gain better accuracy and idea of how the height above sea level, for example, would play a role here. Then you can look into possibly simulating the neutrinos as well. And you can look into possibly simulating some of the angular dependence, because for the time being, we simply assumed most of them were coming from a vertically upwards direction. And of course, lastly, you can, of course, climb the mountain and go measure the muon counts to see if what you're doing is realistic. And right, I have some references, but that's about where it ends. So that was a bit short, but I'm expecting a lot of questions. So.
Yeah, thank you very much for that. If anyone has any questions, please feel free to ask. Okay, I have a question.
Sure.
You're talking about infrared divergence?
Briefly, yes.
So do I understand it correctly? But you said you cut off the muons above a certain momentum.
No, I cut off secondary particles below a certain momentum.
Okay. Below a certain momentum.
Yes, it's a momentum or range. You can sort of switch between the two. So it's just, if I would produce a photon of a range of 3 meters, for example, I'm not going to get any insight out of that, so I might as well not generate it and just mark the energy as lost to the medium instead.
That figure, the colorful one, the second one.
Yeah.
So this is one energy over the size of the Earth, right?
Yes.
So is the color going from blue to green, the first color, going from blue to green? Is that a statistical distribution of energy detect? Or?
It should definitely be. I didn't have time to look into it then, but yes, you do see there are very few high energy muons that come through over there, and absolutely.
So is that why you're taking all of these different energy ranges?
Yes, but I do also think, let me just double check. Yes, that is the case, but it's also a matter of this is sort of an overlay of all the different energies that we started with.
I also have another question.
Sure.
So how this whole practical, like how would they build the lab? Like how do they want to do it? In the middle of the tunnel, have like a turn off and then you go to the lab. Like
pretty much something like that, yeah. There are some labs like this, Grand Sasso and Bodan, which are basically you have a side tunnel, and then in that side tunnel you have a turn off to a large lab facility of a couple of 100 meters. And yeah, so it's more of an engineering problem, but yes, you just turn off. Yeah.
Said that they were interested in building you that on this site in the south next to this outfit.
Yeah.
So other than right here, what alternatives would this be compared against? Where else might they build it and how?
If memory serves, there is one in approval stage. There are considerations for it in Australia, definitely, and I briefly recall seeing one in Argentina based on, or in South America somewhere. I think it was Argentina. It's been a while, sorry, but yeah, basically just those two countries, because this is a massive project that requires some state funding and state assistance, intervention, cooperation is the better word, yes.
How do we stack up?
I can't tell you honestly. I think the Australian one's going a bit faster, but I think they might be looking into something different, for example. So it's basically like dark matter and dark energy and neutrino simulations. I also saw something about double beta decay, but yes, it's a very broad scope of the facility would have a very broad scope, so to speak. So even if there are multiple such facilities, they could all be looking into different things.
So just attaching to that question, what
what variables in measure, able to measure, and complementary rules? Why would you want to build here rather than anywhere? There's a specific issue about Southern Hemisphere. Is this about South Africa trying to get on the map? Is this political? Is this something like physics?
I think it was just a case of, in the Northern Hemisphere, the flux is more or less the same, but it's always, yeah, it's not really any particular reason that I can recall, but you do sort of want to investigate at least, because, you know, currently all of these facilities are sort of in the Northern Hemisphere just by geopolitical, economic reasons.
For example, there's no direction dependence whatsoever, except of course up is up and down is zero flux. Right?
Yes, pretty much, but you should be able to detect something different because you're looking at some different areas of the sky, so to speak.
But I mean,
yeah.
One's
yeah.
Power, so
yeah. So no, it is.
So what are you measuring? What is the purpose of the hidden muon? You don't know where it comes from. You just know it derives from a certain energy.
Yes.
So you're measuring energy.
Yes, energy, and if they arrive or do not, yes.
So what are learning from
that? What will you learn? Well, you'll learn what kind of noise to account for in your experiments. Because these experiments are...
This is your geometry, but what would the detector...
The physical detector.
Yeah.
That will be very difficult. I'm not sure what the energy range on our muon detectors here are, but some of these muons have quite high energies, and I'm not sure exactly what our scintillators are adjusted to.
In our administrator, the guy comes to me and says, "500 million rand." I say, "What are we getting?"
Fair. Research facility that's in the Southern Hemisphere in South Africa. I'm not too sure. Didn't study the marketing pitch as well.
Just to understand something, with this, you spoke about noise reduction in the facility. Is that what this was about?
That's one of the things you can look at. Yes, because
so the actual facilities you run other experiments.
Yes, definitely. This is focusing.
Is it high energy physics?
Yeah. Among other things. You look very displeased, yes. I think we have a full hour.
First of all, what is X on your
that was just the position relative to our axis origin in Geant. If we want to do it thoroughly, I should very likely have reformulated here in the middle. Yes. We do sit in the tunnel with our detector down here. So our detector sits at like Z is equal to minus 750, I think.
And so you're measuring as a function of X, meaning you are making away from the top of the sandstone cap.
Yes, we're moving left.
The point is what? So you're trying to, what are you doing? So there's more muons coming from the sides and from the top.
Yeah. No, the muons are all coming in. The muon, we're sending the same amount of muons from this position downwards towards the tunnel than we are from this position. Yeah. More of them get through here because there's a thinner overburden. Yes.
So you're trying to get as many muons as possible?
Not particularly. We're just trying to find out what would we get if we physically go to the tunnel.
But what the answer that you Geant gives, what question answer?
that answers what is the muon flux if you go sit in the bottom of the tunnel.
So the detector experimentalists will look at that and say, what would that? Could that take that? You're telling them so many muons coming in, so now what they do with that?
That depends on the nature of the experiment, I'm afraid. So.
Yeah, but the scientific presume they will know what sort of protection they need for the lab, to be able to buy it.
No, I mean, we are right here, so we're not dying yet, so it's like, that's something.
No, not.
We also interfere with those. So we know if we can quantify how many muons are in. I don't know how you do it.
Background? Yes, we're trying.
Background flux.
Background? Yes. No, this is cosmic fluxes that's coming in at all time from space.
But are you the experiment was cosmic rays experiment?
No, No, this isn't the experiment. This is investigating into how that flux what the flux would be at the bottom. So other people. Yes. So if someone goes sitting there with a dark matter detector, for example, and they need to take into account how many high energy particles are passing through your beams, that they can do that or use this to possibly classify or analyze the noise in the data. Alternatively, it could also just be that some computational systems have occasional faults because of high energy cosmic particles, and you might want to take that into account as well. But that's kind of tangential.
How does the cross-section go?
Function of energy,
You have this one.
yeah, this one.
So, this is stopping power, it's not bremsstrahlung.
Yes, this is the stopping power, and the radiative losses, if memory serves, is dominated by the bremsstrahlung.
So that's upwards, that's bremsstrahlung.
Yes, this is bremsstrahlung, photonuclear, and what's the other one? Pre-production.
Anything below 1 TeV is no bremsstrahlung.
Very little bremsstrahlung, yes. Below 100 GeV, it looks like there's none, or at least comparably little. So yeah, this is a measurement of the stopping power. So this is how, well, this is in, okay, this is in mass stopping power. So you need to divide or multiply by the density to get back to normal units. But the point of this is just to show that for a particle of that energy moving through 1 meter of copper, it would lose about this many MeV worth of energy to here dominated by inelastic collisions of the electrons and here dominated by those radiative processes. It is just what it is, but ideally you don't want a lot of noise in your system, so you'd want a high stopping power. So you can look, this is for copper. So if you look at it for something like lead, for example, it should all just shift up. And then you'd have a better stopping power and less environmental noise making it to the lab. Yes.
So this is not on mountain.
Afraid not, no. You can try. I mean, if you go sit in a copper mine, you can probably use this for something. But yeah.
Obviously, you don't know what this function looks like on mountain.
It's not, where's the beta block formula? You can adjust it for the mountain, and you can go look at, like in the table, lookup table, for example, where I put that, the A and B values are available in the literature. So from that, you can sort of get, the gradient of this line and sort of the height at which the beta block stopping power sort of levels out. So you can get it for something close to a mountain, but it's more, doesn't change that much.
Do you think the shape will change?
Definitely not, no. The shape definitely won't change.
will not change.
No, the shape won't change. It might shift up and down and left and right a tiny bit, but the overall,
That's in particular array.
yes, depending on.
What changes the amplitude?
Amplitude is just simply, I think it's a better block that's the atomic number because there's more electrons to collide with. It's also dependent on the density and, where is it? Every single one of these values would change the amplitude. And yeah, this is also, formula is also expanded a bit more. It's a tiny bit lengthy.
The values of the mountain experimentally determined, or you just use that standard rock?
Yeah. I used this, which was measured. So yeah, I used this type of material for the mountain, which is the granite's pretty close to standard rock, and the sandstone's a bit less dense. So it's comparable to standard rock, yes.
Okay, if anyone else has a question, happy to go on. Otherwise, okay. Thank you, Huguenot.
Cool.